Hello students, welcome to lecture 2 of module number 3. In the last lecture, we discussed about the formation of bipolar junction transistor, which were two types, one is PNP and one is NPN transistor. Then we studied or discussed a little bit about transistor configuration. There is common base, common collector and common emitter configuration, and we decided that for your course curriculum we will continue only with common emitter configuration, leaving apart common base and common collector configuration. Those students which are going to do higher studies in electrical or electronics department, they will have to study all these configurations in their higher studies. Further, we studied how to bias a bipolar junction transistor and how a bipolar junction transistor works in the form of conducting current from emitter to collector by biasing. Also, we discussed about biasing a bipolar junction transistor, and we studied how a bipolar junction transistor works in terms of conducting current from emitter to collector through base. Also, we arrived at the formula logically, not mathematically. We arrived at the formula that the emitter current IE equal to IB plus IC, that means summation of base current and collector current. And I told you to keep in mind that this base current will be in microampere range and emitter and collector current will be in milliampere range, and the base current is the controlling parameter. By controlling the base current for a fixed emitter current, you can opt out for different collector current. That means the base current can be used to control the output current from the input current. The main takeaway of the last class was that a transistor has to be biased in a certain way in which the input junction, that is base emitter junction in case of a common emitter configuration, the input junction has to be forward biased, and the output junction, which is base collector junction in case of a common emitter, which is the input junction, which is a base emitter in case of a common base junction configuration. The input junction, which is emitter base junction for a common base configuration, has to be forward biased, and the output junction, which is base collector junction for a common base junction configuration, has to be reverse biased. And the emitter current is always equal to the base current and summation of the base current and collector current. In today's lecture, we will discuss about bipolar junction transistor characteristics. We will discuss about common emitter characteristics only, and we will use those common emitter characteristics to discuss two device applications. One of those device application is transistor as an amplifier. We'll try to use transistor as an amplifier, and this other device application is switch, where we'll use a bipolar junction transistor as a switch. Now let us discuss about the characteristics of a NPN transistor in common emitter configuration. Following is the circuit diagram of a NPN transistor. This is an NPN transistor. This is emitter, this is base, and this is collector. And since the arrow sign is outward, so it's a not pointing in transistor, that means NPN transistor. This NPN transistor is connected to a input power supply, input battery, which is VBB. This battery is called VBB battery, and a center tap arrangement is there to change the input potential, this biasing potential VB. This biasing potential is fixed, but we can vary this biasing potential by moving this arrow mark or this tapping arrangement over this rheostat. And one microammeter is connected to the base terminal to measure the base current, and since the base current will be in microampere range, one microammeter is connected to the base terminal. 1 milliammeter is connected to the collector terminal, since the collector current will be in milliampere range. And this VCC is the battery which is used to bias the collector emitter junction, that means output junction. This VBB is used to bias the input junction, that means base emitter junction, and this output junction, this VCC battery is used to bias the output junction, which is collector emitter junction. Now as you can see here, this emitter terminal is both common to both input and output. This is the input section, this is the input section, and this is the output section, and the emitter terminal is common to both input as well as output. This is the circuit diagram which is used to plot the characteristics of a common NPN transistor in common emitter configuration. Now this is a voltmeter which is required to measure the potential VBE, this potential difference between the base terminal and emitter terminal, and here is the voltmeter which is required or which is used to measure the potential between collector and emitter. So this voltmeter VCE is measuring the collector to emitter potential, and this voltmeter VBE is measuring the base to emitter potential, and the base current is into the transistor, emitter current is out of the transistor, and collector current is also into the transistor. That means this emitter current is the summation of base current and collector current. Now this is the characteristics which is called input characteristics. That means the input section of this circuit diagram is behaving in this way. This is a characteristics behavior of the input section of this transistor. What is this characteristics behavior? For this we plotted the base current IB, this base current IB which is measured through this microampere, to the base to emitter voltage, to this base to emitter voltage. That means if we are changing the base to emitter voltage, how this base current is changing, that's what is given by this input characteristics. This input characteristics is giving how the base current is changing with respect to the change in base to emitter voltage, the base to emitter voltage for a fixed collector to emitter potential. For a fixed collector to emitter voltage, how this base current is changing with base to emitter voltage. Now it's pretty clear that there is a barrier potential here in this junction, base to emitter junction. There is a barrier potential depending upon the type of material, that can be either 0.7 volt or a little bit more than that, depending upon the concentration of dopant also. So obviously it is less than 1, so around 0.7 volt. This base to emitter potential, barrier potential, is 0.7 volt for this junction. Now when you are supplying this biasing potential, that is going to balance this base to emitter potential because it is forward biased. This base to emitter junction is forward bias, because this is the positive terminal of the battery, okay, and this is the negative terminal of the battery. So this is positive and this is negative, and therefore this is the forward bias. This junction is forward bias and this junction is reverse biased. Now, due to forward biasing, the barrier potential will go on decreasing, the depletion layer will go on decreasing, and finally at some voltage that will be vanished. And what could be that voltage? That will be around 0.7 volt. So till 0.7 volt the base current will increase slowly. Till 0.7 volt the base current will increase slowly, because the barrier will obstruct the movement of majority charge carrier as in PN junction. Now once the barrier potential will be vanished or will be balanced by this biasing potential, once the barrier potential will be balanced by this biasing potential, then the current will increase suddenly, sharply. That's what is visible in this figure. As you can see, till the moment around 0.6 or 0.7 or 0.8 volt, the current is increasing very slowly. The base current is increasing very slowly. Once the value of barrier to base to emitter voltage, the value of base to emitter voltage is increasing than 0.7 volt, then the base current is increasing sharply. And for each collector to emitter potential, the base current will be different. That means that will depend upon how you are sweeping out the base current, how you are sweeping out the how you are supporting the recombination of electrons and hole in the base. So as you are changing the collector to emitter voltage, as you are changing the collector to emitter voltage, the base current is decreasing. If you are increasing the collector to emitter voltage, more and more number of electrons will be swept out towards the collector and less number of electrons and holes will be combined. So say as the barrier this collector to emitter potential is increasing, this base current is decreasing. So this is the input characteristics and this is the output characteristics. In case of output characteristics, we measure the collector current IC using this milliammeter, and we plot with respect to VCE, which is collector to emitter potential, which is being measured by this voltmeter. For different values of base current, for fixed value of base current, we measure the collector current with respect to collector to emitter potential. Now in this figure you can see that as for a zero base current, that means if the base current is zero, that means there is no potential or there is no biasing potential VBB is there, and hence base current is zero. If the base current is zero, that means what? No electrons or holes are coming from emitter towards collector. That means there is no collector current. If the base current is zero, collector current has to be zero, because there is no biasing potential and no electrons are getting generated by the emitter. Hence the collector current will also be zero. So this figure is showing that the collector current is zero. Whatever may be the collector to emitter potential, the collector current will remain zero as long as the base current is zero. Now if the base current is increasing, the collector current obviously will increase, but that increase will follow certain pattern. What is that pattern? Initially the collector current will increase slowly, and at certain point it will saturate. After that it will not change much with the change in the collector emitter potential. This shows that as you increase the collector to emitter potential, that will start pulling the holes or electrons from the emitter through the base, and that will pull a maximum number of electrons. Which is being sent by this emitter. And since the number of electrons sent by this emitter is depending upon since the number of electrons sent by this emitter is depending upon this VBB potential, therefore the current pulled by this collector to emitter potential, this VCC, current pulled by this VCC will be fixed, that will be saturated. So till that moment current will increase. After that there will be very less dependency of current with respect to VCE voltage or with respect to this VCC voltage. And this region is called saturation region till the moment at which the collector current is increasing with respect to base to a collector to emitter potential. That region is called saturation region. And in this region where the collector current is 0 irrespective of this collector to emitter potential, that is called cutoff region. And the rest of this region is called active region. Beyond active region, if you are increasing the VCE potential, which is reverse biasing this collector to emitter junction, what will happen? Eventually the collector to base junction depletion layer will increase to a very large value, and a avalanche breakdown will take place. As in case of reverse biasing a PN junction, a avalanche breakdown will take place if you will increase the reverse biasing potential of this collector to base junction. And in that case, the collector current will increase sharply to a very large value for each value of base current, and that region is called breakdown region. And of course we should not operate our transistor in this breakdown region, because once the transistor is breaking down, you won't be able to get it back. So always we use the transistor beyond or before this breakdown region. We avoid to use the transistor in the breakdown region. So basically there are three regions which are useful. One is saturation region, in which the collector current is largely or very sharply depending upon collector to emitter potential. That means for a very small change in collector to emitter potential, there is a very large change in collector current. Beyond this saturation region, the change in collector to emitter potential is not changing the collector current much, and that's called active region. And the region in which the collector current is remaining 0, whatever may be the value of collector to emitter potential, that region is called active region. Now we'll study two device applications, in which one will be using this active region for operation, and another device will be using this saturation region and cutoff region for operation. The device application which will use this active region for operation is called amplifier, and the device which will use the saturation region and cutoff region both for its application or for its use, that's called switch. So we'll discuss these two device application next. So students, now let us see how to design an amplifier from the characteristics curve of a transistor. For that, let us consider that, or let us assume that this is the output characteristics of a particular transistor which we are going to use as an amplifier. Now in this output characteristics, there are three regions as we discussed. One is cutoff region, one is saturation region. This region is called saturation region, and this region is called cutoff region, and this region is called active region. And we discussed that, and I told that for use as an amplifier, for the transistor to be used as an amplifier, we need to use it in the active region only. Okay, now in this characteristics we need to plot one load line. What is load line? We have this equation VCE equal to VCC minus ICRL, which is valid for a common emitter transistor, isn't it? Where VCE is the collector emitter resistance, just now we studied, and VCC is the collector biasing potential, and IC is the collector current, and RL is the load resistance. Now since this transistor, since this is the characteristics of this transistor, the entire characteristics will obey this law, right? This characteristics has to, or this transistor has to obey this characteristics as well as this rule or this equation. Now consider VCE equal to 0. When VCE equal to 0, when VCE will be equal to 0, then what will be the value of IC? What will be the value of IC? IC will be equal to VCC divided by RL. Okay, when VCE will be equal to 0, IC will be equal to VCC divided by RL. And if you calculate, that value will give you the maximum value of collector current. The maximum value of collector current will come for a case when VCC CE will be equal to 0. At this point when VCE will be equal to 0, IC will be having maximum value. Now we have chosen the value of RL, the load resistance we have chosen, and the transistor we have chosen, VCC also we have chosen. Okay, now a transistor is deciding only this collector current IC, and that is also being decided according to these values of VCC and RL and VCE. Now at some point of time, if VCE will be equal to 0, then the maximum value of, or the value of collector current will be maximum, and its value will be given by IC will be equal to VCC divided by RL. Now for a particular case, suppose that value of IC maximum, which is IC equal to VCC divided by RL when VCE equal to 0, that is saturation region. Suppose that value is 9.2 milliampere. That value is 9.2 milliampere. Now consider another case. Consider a case when when IC equal to 0, when this collector current will be equal to 0. When this collector current will be equal to 0, then VCE will be equal to VCC, right? Because if IC equal to 0, then this entire term will become 0, and VCE will be equal to VCC, that is the maximum value. And suppose that maximum value is 12 volt. Suppose that maximum value is 12 volt we calculated for our particular configuration. So when IC equal to 0, VCE equal to VCC. Now if you will join these 2 points, one point is in the saturation region, okay, which is giving you the maximum value of collector current, and one point is in the cutoff region when there is no collector current and you are getting the maximum value of VCE, which is equal to VCC. So this is the point in cutoff region, this is a point in the saturation region, and these 2 points, the value of these 2 points obviously depend upon the load resistance RL and this value VCC. These 2 points, the value of these 2 points depend upon 2 things, which we are going to decide, which we are going to put. VCC also is supplied by us, and RL is also supplied by us, that is not given by the transistor. So these 2 entities are deciding the value of IC maximum and VCE maximum, which is equal to VCC. Now if you will join these 2 lines, if you will join these 2 points, now if you will join these 2 points, you will get a line. That line is called load line. Now the load line depend upon 2 things, one is VCC and one is RL. Depending upon RL and VCC, the slope of the load line will change, the values of this maximum points will change. If suppose RL is changing, then RL is increasing, then IC will decrease and the load line will change. If RL is decreasing, IC will increase and load line will change. Similarly, if VCC is increasing, then VCE will increase and the load line will go in this direction. If VCC is decreasing, then VCE will also decrease and the load line will go in this direction. So depending upon the value of VCC and RL, the slope of the load will be changed. Okay, that's why it is slope of this line will be changed, and that's why it is called load line. Now once you chosen the load line, once you decided the load line, you have to choose a quotient point. Okay, the quotient point we generally choose at the middle, so that over that we can load the input signal. Okay, so choose a quotient point Q. Okay, this Q point, quotient point, exactly at the middle of this load line, exactly on the middle of this load line, so that we'll have maximum liberty for a change in the input voltage. Okay, then you'll realize those points slowly. Okay, now choosing that as a quotient point, now suppose I am giving a input, I am giving a change in current IC. Okay, now depending upon that quotient point, I am giving a change in current. Okay, now depending upon that, now putting that load point at the center, suppose I am giving a change in the output voltage. This is the change in the output voltage or output current I am getting, or change in the output voltage I am getting across or in between collector to emitter. Okay, now now putting the Q point or this point at the middle, suppose I am getting a change in the voltage between collector to emitter, VCE. Okay, that change in voltage is from here to here. Now corresponding to this change in voltage, I'll get a change in base current, right? I'll get a change in base current. This is the corresponding change in base current, and this is the corresponding change in collector current. This is the corresponding change in collector current, this is the corresponding change in base current, and this is the corresponding change in collector to emitter potential. Now this collector to emitter potential is the output. Collector to emitter potential is the output. Now corresponding to this output, what is the amount of base current, change in base current I am getting? Base current is changing from, suppose this collector to emitter potential is changing from 5.8 to 9.34 to 2. That means maximum variation, middle point is Q point is 5.8 volt. This quotient point is 5.8 volt for VCE, and the maximum variation is up to 9.34 volt, and the minimum variation VCE minimum is 2 volt. So this is the entire variation of collector to emitter potential. Now corresponding to this collector to emitter potential, what would be the change in the base current? So this is the change in the base current. From where to where this base current is changing? Base current is changing from here to here. This is the minimum value of base current, which is 20 microampere around. This is the minimum value of base current, which is around 20 microampere, and this is the maximum value of base current, which is around 80 microampere. Okay, so in order to get this variation in collector to emitter potential, we need to have a variation in base current, which is from 20 microampere to 80 microampere, and correspondingly we have to get a variation in collector current, which is going from 2 milliampere to 7.7 milliampere. Let me repeat again. For this variation of collector to emitter potential, okay, this variation means around 7.34 volt variation. For this variation of collector to emitter potential, 7.34 volt variation of collector to emitter potential, we must have 2 to 7.7 milliampere variation of collector current, and 20 to 80 microampere variation is in base current. Okay, this is the calculation. This is the calculation we are getting from this output characteristics. Now we got the base current, okay, but base current is not the input. Who is input? Input is base to emitter potential. VBE is the input, right? Base to emitter potential is the input. So we need to relate the input voltage VBE with the output voltage VCE. Now using output characteristics, we have been able to relate the output voltage with the input current. This base current is the input current. Using the output characteristics, we have been able to relate or make a relation between the output voltage, this is the VC is the output voltage, and IB is the input current, okay. But we need to make a relationship between VCE and VBE, where VBE is the input variation of voltage and VCE is the output variation of voltage. For that, we have to relate somehow this base current with this base to emitter voltage. For that, we need input characteristics. Now this is the input characteristics. Now here for this quotient point, we know that VC equal to 5.8 volt. So we need to choose VC equal to 5.8 volt for this curve of input characteristics. Suppose VCE equal to 5.8 volt. Now in this characteristics, we have chosen the quotient point. Value of the base current as 46 microampere. So choose the quotient point value of 46 microampere here. This is suppose 40, this is 60, this is around 50. So suppose this is 46 to 47 microampere value is the quotient point. This is the stable point or DC point we sometimes used to say, okay. Now on this DC point, we will have a variation of base current which is going from 20 microampere to 80 microampere. So we need a variation of base current from 20 microampere to 80 microampere. So this is 20 microampere base current and this is 80 microampere base current, right? So we need a base current variation from 20 microampere to 80 microampere. This is the base current variation from 20 microampere to 80 microampere. Now what will be the corresponding base to emitter voltage? So this x-axis is giving you the base to emitter voltage. So this is the base to emitter voltage, this is the base to emitter voltage corresponding to the base current variation. This is the base to emitter voltage variation corresponding to this base to base current variation. The base current variation is from 20 microampere to 80 microampere, for which the corresponding variation in base to emitter voltage will be this one, which is going from around 0.52 to 0.78, okay. So 0.52 to 0.9 or you can say 0.6 to 0.9. So for 0.3 volt, just mind this or just listen this number carefully. For a variation of 0.3 volt approximately, you are getting a variation in the output of 7.34 volt. Here the variation of VBE is happening from around 0.6 to around 0.9 for a corresponding variation of base current from 20 to 80 microampere. And for this variation of base to emitter voltage, which is nothing but input for us, the corresponding variation in the collector to emitter voltage, which is nothing but output for us, is 7.34 volt. For a variation of base to emitter voltage of 0.3 volt around, or 0.34 volt, you can say 0.34 volt, you are getting the corresponding variation in the output voltage, which is equal to 7.34 volt. So isn't it, it is amplifying. So the variation in input voltage, for a variation in input voltage of 0.34 volt, you are getting a corresponding variation in the output voltage, which is around 7.34 volt. So the output signal is the amplified version of the input signal. Output signal is the amplified version of the input signal. This is the process in which we design our amplifier depending upon how much factor we want to amplify the input signal. Depending upon that, we choose different parameters, the load resistance, the battery supply, VCC and all, so that we can plot this load line. This load line we can plot, and on that load line we will decide a quotient point, and depending upon the quotient point we will fix the value of VBB, and so that we can have exactly that value of quotient point Q, and on that we will overload a AC signal which can be amplified at the output as VCE. So this is the way we used to design an amplifier. Okay, I understand this is little bit difficult to grasp or understand for time being, but still if you get any doubt in this, you can put me a message. I can help you out to understand this more properly, and I can explain you again and again. That's not a issue, but this is the way to explain, this is the way to design an amplifier. Okay, now let us see for a amplifier what are the gain factors. Okay, who is deciding the gains, how much gain, how many time the output signal will be amplified to the input signal, what will be the amplification factor, what will be the gain, those things. Let us study about those things. Now, gains in a common emitter amplifier, there are two gain. One is called current gain, one is called voltage gain. And if you know the current gain and voltage gain, obviously you can easily find out the power gain because power equal to voltage into current. Now, current amplification factor means how many time the amplification is happening. That current amplification factor is again two type. One is called DC current gain, one is called AC current gain. Now, DC current gain, it is the ratio of the collector current IC to the base current IB at constant collector to emitter voltage. The DC current gain is defined as the ratio of the collector current IC to the base current IB at constant collector to emitter voltage. If we write in the form of formula, the DC current gain is denoted as beta DC, which is equal to IC divided by IB at constant collector to emitter potential VCE. This factor you can calculate this beta DC, which is DC current gain, means how much your DC current is getting amplified at the output for a particular input. Who is input current? IB is the input current for the common emitter amplifier. IB base current is the input current for common emitter amplifier, and collector current is the output current. Now, for a particular value of base current, how much collector current you are getting, that is going to decide the amplification factor for DC current. So this can also be found out from the characteristics plot, this output characteristics plot. From this output characteristics plot, as you can see, for 40 microampere, the AC current, collector current, this 40 microampere is the base current. For 40 microampere of base current, you will get the collector current around 7.5 or something. Okay. Similarly, you can find out for 20 microampere, you are getting collector current around 3 point something. So if you divide these values 3.5 to 20 microampere, 3.5 milliampere to 25 microampere, then you will get the DC current gain. Okay, so the DC current gain is nothing but suppose for 6 milliampere, it is calculating for 6 milliampere, the DC current is gain point is suppose 30 microampere. For 6 milliampere, suppose for this 6 milliampere, the DC base current is 30 microampere. So the DC gain can be written as 6 milliampere by 30 microampere, which is equal to 200, which is equal to 200. Here also it is 8 divided by 40 microampere, which is equal to 200. And the AC current gain, so the DC current gain you can find it out from the this characteristics, output characteristics. Similarly, the AC current gain, it is the ratio of the change in collector current delta IC to the change in base current delta IB at constant collector to emitter voltage. So AC current gain is defined as the ratio of the change in collector current delta IC to the change in base current delta IB at constant collector to emitter voltage. Now in this can also be mathematically represented as beta AC, which is equal to delta IC divided by delta IB at constant voltage VCE. And this can also be found out from this plot. In this plot, if you'll see in this plot, if you will see in this plot, the change in base current is from 20 to 40 microampere. Suppose the change in base current is from 20 to 40 microampere, okay, and the corresponding change in collector current is from 8 milliampere to 4 milliampere. So for a change in base current, of 20 microampere, you are getting a change in collector current of 4 milliampere. Okay, so 8 minus 4 milliampere divided by 40 minus 20 microampere, and this is going to give you the AC current gain. Okay, so the AC current gain is equal to 200 like the DC current gain. So this AC current gain and DC current gain you can find out from the output characteristics or this characteristics, but this AC current gain will change once you decide the load line. Once you decide the load line, this AC current gain may change. Okay, that will depend upon the load line after that. Now if the load line is this one, then the AC current gain is equal to DC current gain. That's not an issue. But if you are putting a load line, then AC current gain will be different than the DC current gain. Now the voltage gain, let's discuss about the voltage gain. Now AC voltage gain is the ratio in the output voltage, collector voltage delta VCE to the change in input voltage, that is applied signal voltage delta VI. So the ratio of the collector voltage, change in the collector voltage, output collector voltage, which is equal to delta VCE, to the change in input voltage or applied signal voltage, which is equal to delta VI, is called AC voltage gain. Now it is mathematically defined as AVAC, where AV stands for current gain and AC stands for AC signal, delta V output divided by delta V input. But this delta V output can be written as delta IC into R naught. Okay, R out. Here R out is nothing but the load resistance RL. So this delta V output can be written as change in the collector current into load resistance, which is nothing but the output resistance, sometime we used to say, and delta VI can be written as, which is nothing but VBE. Delta VI can be written as change in base current into input resistance RI. Change in base current into input resistance RI will give you the delta VI, which is change in input voltage. But what is delta IC by delta IB? Change in output current divided by change in input current, or change in collector current divided by change in base current. That is nothing but the AC gain, AC current gain, right? This is beta AC is nothing but the AC current gain, which is equal to delta IC divided by delta IB. Okay. Now if we'll substitute that as beta AC, then beta AC into RO divided by RI. Beta AC into RO divided by RI. So by if you know beta AC, then we can easily find out the voltage gain, AC voltage gain, just by knowing the value of output resistance and input resistance. Okay, that's why it is also called as transfer of resistance. That is the reason here we are transferring the resistance from input to the output. That's why it is called the transfer of resistor. So if you know the resistances, output resistance and input resistance, then you can easily find out the voltage gain, AC voltage gain, if you know the AC current gain. Okay, just by multiplying the AC current gain with the ratio of the output resistance to the input resistance. Okay, now what is AC power gain? Now it is the ratio of the change in output power to the change in input power. Okay, now who is the output power here mathematically we can write the power gain AP, AC power gain AP is equal to delta P output divided by delta P input. Now how to write power? Power is nothing but current into voltage. So power I can write as delta V output into delta IC. Okay, what is delta V output? Delta V output is the change in the output voltage, and delta IC is the change in output current. So that is the product of those two is going to give you the change in output power. Similarly, delta Vi is the change in input voltage, and delta Ib is the change in input current, and their product is going to give you the change in input power. Okay, since power equal to current into voltage. Now what is delta IC by delta IB? That is again beta IC, right? Delta IC by delta IB is again beta IC. Again delta VO, V output delta divided by delta V input is again beta IC into resistance gain, right? So delta IC by delta IB is beta IC, resistance current gain, AC current gain, and delta V output divided by delta V input is again current gain, AC current gain into resistance gain. Okay, so there are two beta AC are coming and one resistance gain is coming. So this power gain can be written as beta AC square into resistance gain. So this is the formula for power gain for an amplifier in common emitter configuration. The power gain can be written as the square of the AC current gain, which is equal to beta AC square into resistance gain, This is called power gain formula. So we discussed in detail about how to design an amplifier, the circuit diagram of an amplifier, how it works, and different gain parameters of the amplifier, means DC current gain, how much DC current gain is happening, how much AC current gain is happening, how much AC voltage gain is happening, how much AC power gain is happening. All those things we discussed, and next we are going to discuss about another device application which is called a switch, and that basically operate in the cutoff and breakdown region, cutoff and saturation region. Okay, we'll discuss that in the next slide. So let us now discuss how a NPN transistor can be used as a switch. Switch in the sense, this is same as mechanical switch, on or off. A mechanical switch gives you the two possibilities or two situations. In one case it will be off, in which case it will not conduct any current, and another case it will be switch on, in which case it will conduct current. The same situation we can realize using a transistor electronically, and let's see how that can be done. Okay, now for NPN transistor to behave as a switch, this is the circuit diagram. Okay, this is the NPN transistor which is biased by two batteries. One is VBB, which is biasing the base to emitter junction. One is VCC, which is biasing the collector to emitter junction. Okay, now in this circuit configuration, this Vi is a voltage which is called input voltage, and Vo is a voltage which is called output voltage. Now we know that for any transistor, NPN transistor, the emitter current is equal to the summation of base current and collector current. That we derived using Kirchhoff's law, Kirchhoff's current law. Now ICRL, this ICRL is the potential drop across this resistance RL. Now if you use the Kirchhoff's voltage law in this input segment, in this input circuit, then here it is increasing, this is negative potential and this is positive potential of VBB, and current is flowing in this direction, So here the voltage drop across this resistance RB will be equal to IBRB. Here it is positive, here it is negative, IBRB, and this VBE potential, this depletion layer or barrier potential is called VBE. Here it is positive, or here it is positive, here it is negative, VBE potential. So if I use the Kirchhoff's voltage law, then this VBB will be equal to IBRB, this potential drop across this resistance, plus VBE, this potential barrier potential, VBE, this potential. Okay. So by using Kirchhoff's law in this input circuit, we can write VBB equal to VBE plus IBRB. Similarly, using Kirchhoff's law in this circuit, in this output circuit, we can write VCE that we derived already, VCE equal to VCC minus ICRL. This is VCC, and this is ICRL is the potential drop across this resistance, and VC is the potential drop across this collector to emitter terminal. Okay, so VCE equal to VCC minus ICRL. This equation we already derived earlier. Okay, now what is VBB? VBB is nothing but the input voltage. This input voltage is across this VBB, so VBB is the input voltage. And what is VCE? VCE is the output voltage. This is collector terminal and this is emitter terminal, and we are taking the output across collector to emitter, this output across collector to emitter. So this VCE is the output voltage. Therefore we can write input voltage VI is equal to VBE plus IBRB, which is nothing but VBB, and output voltage as VO, which is nothing but VC, equal to VCC minus ICRL. Okay, now let us plot a curve between voltage, input voltage and output voltage. Now this is a curve between input voltage and output voltage. Now when VI is 0, the input voltage is 0 or 0 to 0.6 volt till the barrier potential is vanishing. Till that point, from 0 to 0.6 volt, when the value of VI will be equal to 0.026 volt, when the value of VI will be equals to in between 0 to 0.6 volt, then what will happen? There will be no base current, because there will be a barrier here in this junction, and no electron will be pushed by this emitter terminal towards the base, and there will be no recombination between electron and holes in the base region. Therefore the base current will be 0. Now if the base current will be 0, then according to this formula, the collector current will also be 0, because since base current is 0, emitter current will be 0, and hence collector current will also be 0. If the collector current is 0, the potential drop across this resistance, which is equal to ICRL, will also be 0. There will be no potential drop across this resistance, since IC equals to 0. If IC equals to 0, there will be no potential drop across this resistance RL, and hence the voltage, output voltage, will be maximum, which is nothing but VCC. Okay, so the output voltage will be maximum, which is nothing but VCC. So in this case, when the value of VI will be in between 0 to 0.6 volt, then the transistor output current will be 0, and this transistor is said to be in cutoff state or cutoff region. That means it is not conducting any current through the transistor. Through the transistor, no current is flowing. That's why it is called in cutoff state. Now in second case, suppose the input voltage VI is somewhere between 0 to 0.6 to 1 volt. From 0.6 to 1 volt, the base current will increase linearly, slowly, and accordingly the collector current will also increase slowly. Okay, for a input potential VI is equal to 0.6 to 1 volt, the base current will also increase slowly, because we are balancing that barrier potential at base to emitter junction, which is around 0.6 to 0.7 volt. Okay, so if it is 1 volt, if it is more than 0.6 volt, then there will be a base current, and hence there will be a collector current. Now if the base current is increasing linearly, the collector current will also increase linearly, and there will be a potential drop across this resistance which will be linear, which will increase linearly. So this potential drop across this resistance will also increase linearly, since collector current will increase linearly because of this linear increase in the base current IB when the input voltage Vi is more than 0.6 volt or in between 0.6 to 1 volt. So in that case the voltage will drop linearly like this, and this region is called active region of the transistor. This region is called active regions of the transistor. Now when Vi will be more than 1 volt, when Vi will be input voltage will be more than 1 volt, then maximum amount of collector current will be taking place. Wow, the collector current will be maximum. When Vi will be more than 1 volt, collector current will be maximum. Okay, if the collector current will be maximum, the potential drop across this resistance will be maximum, and hence the output VO, which is equal to VCC minus ICRL, will be minimum. If IC is maximum, then V output, which is equal to VCC minus ICRL, will be minimum. VCC. Okay, now if Vi is more than 1 volt, then collector current will be maximum, and hence the potential drop across this resistance IC will be, the resistance RL will be maximum, because ICRL will be maximum, and the output voltage will be minimum, though that will not be 0 at all until and unless this breakdown is happening, but this voltage will be minimum, and that region is called saturation region. Okay, so there are two possibilities. If we will exclude this active region, there are two possibilities. When the input voltage is less than 0.6 volt, the transistor is in cutoff state. This transistor is in cutoff state, that means it is not conducting current. And when the input voltage is more than 1 volt, then the transistor is in saturation state or saturation region, that means it is conducting maximum amount of current. So if you will consider this as a switch off state, this cutoff state as a switch off state where no current is flowing, we can consider this state, saturation region, as the switch on state where maximum amount of current is flowing. So this, in this way, this NPN transistor can be used as a switch where it can behave as a switch off state. It can remain in switch off state when the input voltage is less than 0.6 volt, and it will come to a switch on state when the input voltage is more than 1 volt. Okay, so that's how it is behaving as a switch. Now let us recall or let us recap what we discussed now. Now let us recap what we just discussed here. Now let us recap what we discussed here. Now in case 1, when Vi is less than 0.6 volt, there is no collector current. Okay, when Vi is less than 0.6 volt, because of the barrier potential of the base to emitter junction, there will be no collector current, and hence equation 4 will give you V output will be equal to VCC. So the output voltage will be maximum, and in this situation the transistor is said to be in cutoff state because it is not conducting any current. Now in case 2, when the input voltage is more than 0.6 volt and less than 1 volt, the collector current IC increases linearly with voltage. Okay, hence from equation number 4, V output decreases linearly and the transistor is said to be in active region. Okay, in case when the voltage, input voltage is between 0.6 volt to 1 volt, the collector current IC increases linearly with voltage, and hence the output voltage V output decreases linearly and the transistor is said to be in active region. Now in case 3, when Vi equal to 1 volt or Vi is greater than 1 volt. Now in case 3, when Vi is greater than 1 volt, V output is found to decrease towards 0 but not 0. V output found to decrease towards 0 but not 0, because the collector current is maximum. It is not in breakdown region anymore. It is not in the breakdown region, though it is giving the maximum amount of current. It is not in the breakdown region. Therefore, the output voltage will not be 0, though it will be minimum. It will go towards 0. So when Vi is greater than 1 volt, V output is found to decrease towards 0, but not 0. The collector current IC becomes maximum and the transistor is said to be in saturation state. Okay. Therefore, in cutoff state, when Vi is low, the transistor is not working and hence is said to be in switched off state. In cutoff state, when Vi is low, less than 0.6 volt, the transistor is not working, means it is not conducting any current, and hence it is said to be in switched off state. In saturation state, when Vi is high, more than 1 volt, the transistor is fully conducting as IC is nearly equal to maximum and the transistor is said to be in switched on state. And this is how a transistor is used or is working as a switch. Now, what is the difference between the mechanical switch and this electronic switch? How we are using or why you are using electronic switch? In case of mechanical switch, the switching speed will be limited. Okay, that will be limited by the human being. With maximum how many rate, how much rate you can switch on or switch off a mechanical switch, that will be maximum 30 times per minute or sometime 60 times per minute. But the electronic switch can be used to switch on, to operate in switch off and switch on state maybe 6000 times per minute or more than that. So this switching rate of electronic switch is quite more than the mechanical switch, which is limited by the human being. So the mechanical switch will be, the switching speed of the mechanical switch will be limited, but the switching speed of the electronic switch will be far more than that of the mechanical switch. That's why we use electronic switch, which is required particularly in computers or computation. Okay, so this is the end of this module where we discussed about transistor, the construction of a transistor, how to bias a transistor, how a transistor work, and then we studied the characteristics of a transistor, and those characteristics we further used to design or to study about the application of transistor as a amplifier and as a switch. So in next module we'll discuss or we'll study about digital electronics. Thank you.